Hello again, this is Teacher Todd, and we're on to Chapter 6. Transport Level Security. The topic of web security is a broad one and can easily fill a book. In this chapter, we begin with a discussion of the general requirements for web security, and then focus on 3 standardized schemes that are becoming increasingly important as part of the web commerce and the focus on security at the transport layer. SSL/TLS, HTTPS, and SSH. Web security considerations. The World Wide Web is fundamentally a client-server application running over the Internet and TCP/IP intranets. As such, the security tools and approaches discussed so far in this book are relevant to the issue of web security. However, the following characteristics of web usage suggest the need for a more tailored security tool. Although web browsers are very easy to use, web servers are relatively easy to configure and manage, and web content is increasingly easy to develop. The underlying software is extraordinarily complex. This complex software may hide many potential security flaws. The short history of the web is filled with examples of new and upgraded systems, properly installed, that are vulnerable to a variety of security attacks. A web server can be exploited as a launching pad into the corporation's or agency's entire computer complex. Once the web server is subverted, an attacker may be able to gain access to data and systems not part of the web itself, but connected to the server at the local site. Casual and untrained in security matters, users are common clients for web-based services. Such users are not necessarily aware of the security risks that exist and do not have the tools or knowledge to take effective countermeasures. This table provides a summary of the types of security threats faced when using the web. One way to group these threats is in terms of passive and active attacks. Passive attacks include eavesdropping on network traffic between browser and server and gaining access to information on a website that is supposed to be restricted. Active attacks include impersonating another user, altering messages in transit between client and server, and altering information on a website. Another way to classify web security threats is in terms of the location of the threat: web server, web browser, and network traffic between the browser and server. Issues of server and browser security fall into the category of computer system security. Part 6 of this book addresses the issue of system security in general, but is also applicable to web system security. Issues of traffic security fall into the category of network security and are addressed in this chapter. A number of approaches to providing web security are possible. The various approaches that have been considered are similar in the services they provide and, to some extent, in the mechanisms that they use, but they differ with respect to their scope of applicability and their relative location within the TCP/IP protocol stack. The figure illustrates this difference. One way to provide web security is to use IP security, IPsec. The advantage of using IPsec is that it is transparent to end users and applications and provides a general purpose solution. Furthermore, IPsec includes a filtering capability so that only selected traffic need incur the overhead of IPsec processing. Another relatively general purpose solution is to implement security just above TCP, as in the figure. The foremost example of this approach is the Secure Sockets Layer, SSL, and the follow-on internet standard known as Transport Layer Security, TLS. At this level, there are 2 implementation choices. For full generality, SSL or TLS could be provided as part of the underlying protocol suite and therefore be transparent to applications. Alternatively, SSL can be embedded in specific packages. For example, Netscape and Microsoft Explorer browsers come equipped with SSL, and most web servers have implemented the protocol. Application-specific security services are embedded within the particular application. In the figure C shows an example of this architecture. The advantage of this approach is that the service can be tailored to the specific needs of a given application. One of the most widely used security services is Transport Layer Security, TLS. The current version is version 1.2, defined in RFC 5246. TLS is an internet standard that evolved from a commercial protocol known as Secure Sockets Layer, SSL. Although SSL implementations are still around, it has been deprecated by IETF and is disabled by most corporations offering TLS software. TLS is a general purpose service implemented as a set of protocols that rely on TCP. At this level, there are two implementation choices. For full generality, TLS could be provided as part of the underlying protocol suite and therefore be transparent to applications. Alternatively, TLS can be embodied in specific packages. For example, most browsers come equipped with TLS, and most web servers have implemented the protocol. TLS is designed to make use of TCP to provide a reliable end-to-end secure service. TLS is not a single protocol, but rather two layers of protocols, as illustrated in the figure. The TLS record protocol provides basic security services to various higher layer protocols. In particular, the Hypertext Transfer Protocol, HTTP, which provides the transfer service for web client-server interaction, can operate on top of TLS. Three higher layer protocols are defined as part of TLS: the Handshake Protocol, the Change Cipher Spec Protocol, and the Alert Protocol. These TLS-specific protocols are used in the management of TLS exchanges and are examined later in the section. A fourth protocol, the Heartbeat Protocol, is defined in a separate RFC and is also discussed subsequently in this section. Two important TLS concepts are the TLS session and the TLS connection, which are defined in the specification as follows. Connection. A connection is a transport in the OSI layering model definition that provides a suitable type of service. For TLS, such connections are peer-to-peer relationships. The connections are transient. Every connection is associated with one session. Session. A TLS session is an association between a client and a server. Sessions are created by the Handshake Protocol. Sessions define a set of cryptographic security parameters, which can be shared among multiple connections. Sessions are used to avoid the expensive negotiation of new security parameters for each connection. Between any pair of parties, applications such as HTTP on client and server, there may be multiple secure connections. In theory, there may also be multiple simultaneous sessions between parties, but this feature is not used in practice. There are a number of states associated with each session. Once a session is established, there is a current operating state for both read and write, i.e. receive and send. In addition, during the Handshake Protocol, pending read and write states are created. Upon successful conclusion of the Handshake Protocol, the pending states become the current states. A session state is defined by the following parameters. Session identifier, an arbitrary byte sequence chosen by the server to identify an active or resumable session state. Peer certificate, an X509 version 3 certificate of the peer. This element of the state may be null. Compression method, the algorithm used to compress data prior to encryption. Cipherspec specifies the bulk data encryption algorithm, such as null, AES, etc., and a hash algorithm, such as MD5 or SHA-1, used for MAC calculation. It also defines cryptographic attributes, such as the hash type or hash size. Master secret, a 48-byte secret shared between the client and the server. Is resumable, a flag indicating whether the session can be used to initiate new connections. A connection state is defined by the following parameters: server and client random, byte sequences that are chosen by the server and client for each connection. Server write MAC secret, the secret key used in MAC operations on data sent by the server. Client write MAC secret, the secret key used in MAC operations on data sent by the client. Server write key, the secret encryption key for data encrypted by the server and decrypted by the client. Client write key, the symmetric encryption key for data encrypted by the client and decrypted by the server. Initialization vectors. When a block cipher in CBC mode is used, an initialization vector, IV, is maintained for each key. The field is first initialized by the SSL handshake protocol. Thereafter, the final ciphertext block from each record is preserved for use as the IV with the following record. Sequence numbers. Each party maintains separate sequence numbers for transmitted and received messages for each connection. When a party sends or receives a change cipher spec message, the appropriate sequence number is set to 0. Sequence numbers may not exceed 2 to the 64 minus 1. TLS record protocol defines two services for TLS connections. Confidentiality. The handshake protocol defines a shared secret that is used for conventional encryption of TLS payloads. Message integrity. The handshake protocol also defines a shared secret key that is used to form a message authentication code, MAC. This figure indicates the overall operation of the TLS record protocol. The record protocol takes an application message to be transmitted, fragments the data into manageable blocks, optionally compresses the data, applies a MAC, encrypts, adds a header, and transmits the resulting unit in a TCP segment. Received data are decrypted, verified, decompressed, and reassembled before being delivered to the higher level users. The first step is fragmentation. Each upper layer message is fragmented into blocks of 2 to the 14th bytes, which is 16,384 bytes or less. Next, compression is optionally applied. Compression must be lossless and may not increase the content length by more than 1,024 bytes. In TLS version 2, no compression algorithm is specified, so the default compression algorithm is null. The next step in processing is to compute a message authentication code over the compressed data. TLS makes use of the HMAC algorithm defined in RFC 2104. Next, the compressed message plus the MAC are encrypted using symmetric encryption. Encryption may not increase the content length by more than 1,024 bytes, so that the total length may not exceed 2 to the 14th plus 2048. For stream encryption, the compressed message plus the MAC are encrypted. Note that the MAC is computed before encryption takes place, and that the MAC is then encrypted along with the plain text or compressed plain text. For block encryption, padding may be added after the MAC prior to encryption. The padding is in the form of a number of padding bytes followed by a 1-byte indication of the length of the padding. The padding can be an amount that results in a total that is a multiple of the cipher's block length, up to a maximum of 255 bytes. For example, if the cipher block length is 16 bytes, for example AES, and if the plain text or compressed text, if compression is used, plus MAC plus padding length is 79 bytes, then the padding length in bytes can be 1, 17, 33, and so on, up to 161. At a padding length of 161, the total length is 79 plus 161 equals 240. A variable padding length may be used to frustrate attacks based on an analysis of the lengths of exchanged messages. Please review the figure which illustrates the TLS record format. The change cipher spec protocol is one of the 4 TLS specific protocols that use the TLS record protocol, and it is the simplest. This protocol consists of a single message, which consists of a single byte with the value 1. The sole purpose of this message is to cause the pending state to be copied into the current state, which updates the cipher suite to be used on this connection. The alert protocol is used to convey TLS-related alerts to the peer entity. As with other applications that use TLS, alert messages are compressed and encrypted as specified by the current state. Each message in this protocol consists of 2 bytes. The first byte takes the value warning 1 or fatal 2 to convey the severity of the message. If the level is fatal, TLS immediately terminates the connection. Other connections on the same session may continue, but no new connections on the session may be established. The second byte contains a code that indicates the specific alert. The most complex part of TLS is the handshake protocol. This protocol allows the server and client to authenticate each other and to negotiate an encryption and MAC algorithm and cryptographic keys to be used to protect data sent in a TLS record. The handshake protocol is used before any application data is transmitted. The handshake protocol consists of a series of messages exchanged by the client and server. All of these have the format shown in the figure .c. In this figure, we see the message types. Each message has 3 fields. Type, which is 1 byte, it indicates one of 10 messages, as shown in the figure. Length, 3 bytes, is the length of the message in bytes. Content, the parameters associated with this message, and they're listed in the table. This figure shows the initial exchange needed to establish a logical connection between the client and server. The exchange can be viewed as having 4 phases as shown. Please review the figure. Cryptographic computations. 2 further items are of interest. 1, the creation of a shared master secret by means of the key exchange. And 2, the generation of cryptographic parameters from the master secret. The shared master secret is a one-time 48-byte value generated for this session by means of secure key exchange. The creation is in 2 stages. First, a pre-master secret is exchanged. Second, the master secret is calculated by both parties. For pre-master secret exchange, there are 2 possibilities. RSA, a 48-byte pre-master secret is generated by the client, encrypted with the server's public RSA key, and sent to the server. The server decrypts the ciphertext using its private key to recover the pre-master secret. The alternative is Diffie-Hellman, where both the client and server generate a Diffie-Hellman public key. And using these keys, they create the pre-master secret. In this figure, you can see the algorithm used, or the flowchart. Heartbeat protocol. In the context of computer networks, a heartbeat is a periodic signal generated by hardware or software to indicate normal operation or to synchronize other parts of a system. A heartbeat protocol is typically used to monitor the availability of a protocol entity. In the specific case of TLS, a heartbeat protocol was defined in 2012 in RFC 6250. The heartbeat protocol runs on top of the TLS record protocol and consists of two message types, heartbeat request and heartbeat response. The use of the heartbeat protocol is established during phase 1 of the handshake protocol. Each peer indicates whether it supports heartbeats. If heartbeats are supported, the peer indicates whether it is willing to receive heartbeat request messages and respond with heartbeat response messages, or only willing to send heartbeat request messages. A heartbeat request message can be sent at any time. Whenever a request message is received, it should be answered promptly with a corresponding heartbeat response message. The heartbeat response message includes payload length, payload, and padding fields. The payload is a random content between 16 and 64 kbytes in length. The corresponding heartbeat response message must indicate an exact copy of the received payload. The padding is also a random content. The padding enables the sender to perform a path MTU, maximum transfer unit discovery operation, by sending requests with increasing padding until there is no answer anymore, because one of the hosts on the path cannot handle the message. The heartbeat serves two purposes. First, it assures the sender that the recipient is still alive, even though there may not have been any activity over the underlying TCP connection for a while. Second, the heartbeat generates activity across the connection during idle periods, which avoids closure by a firewall that does not tolerate idle connections. The requirement for the exchange of a payload was designed into the heartbeat protocol to support its use in a connectionless version of TLS known as Datagram Transport Layer Security, DTLS. Because a connectionless service is subject to packet loss, the payload enables the requester to match response messages to request messages. For simplicity, the same version of the heartbeat protocol is used with both TLS and DTLS. Thus, the payload is required for both TLS and DTLS. SSL TLS attacks. Since the first introduction of SSL in 1994 and the subsequent standardization of TLS, numerous attacks have been devised against these protocols. The appearance of each attack has necessitated changes in the protocol, the encryption tools used, or some aspect of the implementation of SSL and TLS to counter these threats. Attack categories. We can group the attacks in four general categories. Attacks on the handshake protocol. As early as 1998, an approach to compromising the handshake protocol based on exploiting the formatting and implementation of the RSA encryption scheme was presented. As countermeasures were implemented, the attack was refined and adjusted to not only thwart the countermeasures, but also speed up the attack. Attacks on the record and application data protocols. A number of vulnerabilities have been discovered in these protocols, leading to patches to counter the new threats. As a recent example, in 2011, some researchers demonstrated a proof of concept called BEAST, Browser Exploit Against SSL TLS, that turned what had been considered only a theoretical vulnerability into a practical attack. BEAST leverages a type of cryptographic attack called a chosen plaintext attack. The attacker mounts the attack by choosing a guess for the plaintext that is associated with a known ciphertext. The researchers developed a practical algorithm for launching successful attacks. Subsequent patches were able to thwart this attack. The authors of the BEAST attack are also the creators of the 2012 CRYME, Compression Ratio Info Leak Made Easy attack, which can allow an attacker to recover the content of web cookies when data compression is used, along with TLS. When used to recover the content of secret authentication cookies, it allows an attacker to perform session hijacking on an authenticated web session. Attacks on the PKI. Checking the validity of the X509 certificates is an attack subject to a variety of attacks, both in the context of SSL TLS and elsewhere. For example, it was demonstrated that commonly used libraries for SSL TLS suffer from vulnerable certificate validation implementations. The authors revealed weaknesses in the source code of OpenSSL, GNU TLS, JSSE, Apache HTTP client, Webernuk, curl, PHP, Python, and applications built upon or with these products. Other attacks. There's listed a number of attacks that do not fit into any of the preceding categories. One example is an attack announced in 2011 by the German hacker group, the Hacker's Choice, and it's a DOS attack, denial of service. The attack creates a heavy processing load on a server by overwhelming the target with SSL TLS handshake requests. Boosting system load is done by establishing new connections or using renegotiation. Assuming that the majority of computation during a handshake is done by the server, the attack creates more system load on the server than is needed, resulting in a denial of service. The server is forced to continuously recompute random numbers and keys. The history of attacks and countermeasures for SSL TLS is representative of that for other internet-based protocols. A perfect protocol and a perfect implementation strategy are never achieved. A constant back and forth between threats and countermeasures determines the evolution of internet-based protocols and their related security. HTTPS, which is HTTP over SSL. It refers to the combination of HTTP and SSL to implement secure communication between a web browser and a web server. The HTTPS capability is built into all modern web browsers. Its use depends on the web server supporting HTTPS communication. For example, some search engines do not support HTTPS. Google provides HTTPS as an option. The principal difference seen by a user of a web browser is that URL, Uniform Resource Locator, addresses begin with https:// rather than http://. A normal HTTP connection uses port 80. If HTTPS is specified, port 443 is used, which invokes SSL or TLS. When HTTPS is used, the following elements of the communication are encrypted: the URL of the requested document, contents of the document, contents of browser forms, which are filled in by browser users, cookies sent from browser to server and from server to browser. Contents of the HTTP header. HTTPS is documented in RFC 2818. HTTP over TLS. There is no fundamental change in using HTTP over either SSL or TLS, and both implementations are referred to as HTTPS. Connection initiation. For HTTPS, the agent acting as the HTTP client also acts as the TLS client. The client initiates a connection to the server on the appropriate port and then sends the TLS client hello to begin the TLS handshake. When the TLS handshake has finished, the client may then initiate the first HTTP request. All HTTP data is to be sent as TLS application data. Normal HTTP behavior, including retained connections, should be followed. There are 3 levels of awareness of a connection in HTTPS. At the HTTP level, an HTTP client requests a connection to an HTTP server by sending a connection request to the next lower layer. Typically, the next lower layer is TCP, but it may also be TLS/SSL. At the level of TLS, a session is established between a TLS client and a TLS server. This session can support 1 or more connections at any time. As we have seen, a TLS request to establish a connection begins with the establishment of a TCP connection between the TCP entity on the client side and the TCP entity on the server side. Connection closure. An HTTP client or server can indicate the closing of a connection by including the following line in an HTTP record. Connection close. This indicates that the connection will be closed after this record is delivered. The closure of an HTTPS connection requires that TLS close the connection with the peer TLS entity on the remote side, which will involve closing the underlying TCP connection. At the TLS level, the proper way to close a connection is for each side to use the TSL alert protocol to send a close notify alert. TLS implementations must initiate an exchange of closure alerts before closing a connection. A TLS implementation may, after sending a closure alert, close the connection without waiting for the peer to send its closure alert, generating an incomplete close. Note that an implementation that does this may choose to reuse the session. This should only be done when the application knows, typically through detecting HTTP message boundaries, that it has received all the messages data that it cares about. HTTP clients also must be able to cope with a situation in which the underlying TCP connection is terminated without a prior close notify alert and without a connection close indicator. Such a situation could be due to a programming error on the server or a communication error that causes the TCP connection to drop. However, the unannounced TCP closure could be evidence of some sort of attack. So the HTTPS client should issue some sort of security warning when this occurs. Secure Shell, SSH, is a protocol for secure network communications, designed to be relatively simple and inexpensive to implement. The initial version, SSH1, was focused on providing a secure remote logon facility to replace Telnet and other remote logon schemes that provided no security. SSH also provides a more general client-server capability and can be used for such network functions as file transfer and email. A new version, SSH2, fixes a number of security flaws in the original scheme. SSH2 is documented as a proposed standard in IETF RFC 4250 through 4256. SSH client and server applications are widely available for most operating systems. It has become the method of choice for remote logon and X-tunneling, and is rapidly becoming one of the most pervasive applications for encryption technology outside of embedded systems. SSH is organized as three protocols that typically run on top of TCP. Transport Layer Protocol provides server authentication, data confidentiality, and data integrity with forward secrecy, i.e., if a key is compromised during one session, the knowledge does not affect the security of earlier sessions. The transport layer may optionally provide compression. User Authentication Protocol authenticates the user to the server. Connection Protocol multiplexes multiple logical communication channels over a single underlying SSH connection. Transport Layer Protocol. Server authentication occurs at the transport layer based on the server possessing a public-private key pair. A server may have multiple host keys using multiple different asymmetric encryption algorithms. Multiple hosts may share the same host key. In any case, the server host key is used during key exchange to authenticate the identity of the host. For this to be possible, the client must have a prior knowledge of the server's public host key. RFC 4251 dictates two alternative trust models that can be used. 1. The client has a local database that associates each host name, as typed by the user, with the corresponding public host key. This method requires no centrally administered infrastructure and no third-party coordination. The downside is that the database of a name-to-key association may become burdensome to maintain. 2. The host name-to-key association is certified by a Trusted Certification Authority, CA. The client only knows the CA root key and can verify the validity of all host keys certified by accepted CAs. This alternative eases the maintenance problem, since ideally only a single CA key needs to be securely stored on the client. On the other hand, each host key must be appropriately certified by a central authority before authorization is possible. This figure illustrates the sequence of events in the SSH Transport Layer Protocol. First, the client establishes a TCP connection to the server. This is done via the TCP protocol and is not part of the Transport Layer Protocol. Once the connection is established, the client and server exchange data, referred to as packets, in the data field of a TCP segment. Each packet is in the following format: packet length, length of the packet in bytes, not including the packet length in MAC fields; padding length, length of the random padding field; payload, useful contents of the packet. Prior to algorithm negotiation, this field is uncompressed. If compression is negotiated, then in subsequent packets, this field is compressed. Random padding. Once an encryption algorithm has been negotiated, this field is added. It contains random bytes of padding so that the total length of the packet, excluding the MAC field, is a multiple of the cipher block size, or 8 bytes for a stream cipher. Message Authentication Code, MAC. If message authentication has been negotiated, this field contains the MAC value. The MAC value is computed over the entire packet plus a sequence number, excluding the MAC field. The sequence number is an implicit 32-bit packet sequence that is initialized to 0 for the first packet and incremented for every packet. The sequence number is not included in the packet sent over the TCP connection. Once an encryption algorithm has been negotiated, the entire packet, excluding the MAC field, is encrypted after the MAC value is calculated. The SSH transport layer packet exchange consists of a number of steps. SSH transport layer cryptographic algorithms. This table shows you the allowable options for encryption, MAC, and compression. For each category, the algorithm chosen is the first algorithm on the client's list that is also supported by the server. Authentication methods. The server may require one or more of the following authentication methods. Public key. The details of this method depend on the public key algorithm chosen. In essence, the client sends a message to the server that contains the client's public key, with the message signed by the client's private key. When the server receives this message, it checks whether the supplied key is acceptable for authentication, and if so, it checks whether the signature is correct. Password. The client sends a message containing a plain text password, which is protected by encryption by the transport layer protocol. Host-based. Authentication is performed on the client's host rather than the client itself. Thus, a host that supports multiple clients would provide authentication for all its clients. This method works by having the client send a signature created with the private key of the client host. Thus, rather than directly verifying the user's identity, the SSH server verifies the identity of the client host and then believes the host when it says the user has already authenticated on the client side. Connection protocol. The SSH connection protocol runs on top of the SSH transport layer protocol and assumes that a secure authentication connection is in use. That secure authentication connection, referred to as a tunnel, is used by the connection protocol to multiplex a number of logical channels. All types of communication using SSH, such as a terminal session, are supported using separate channels. Either side may open a channel. For each channel, each side associates a unique channel number which need not be the same on both ends. Channels are flow controlled using a window mechanism. No data may be sent to a channel until a message is received to indicate that window space is available. The life of a channel progresses through 3 stages: opening a channel, data transfer, and closing a channel. Please pause and review the figure, which provides an example of a connection protocol message exchange. Channel types. 4 channel types are recognized in the SSH connection protocol specification. Session. The remote execution of a program. The program may be a shell, an application such as file transfer or email, a system command, or some built-in subsystem. Once a session channel is opened, subsequent requests are used to start the remote program. X11. This refers to the X window system, a computer software system and network protocol that provides a graphical user interface, GUI, for networked computers. X allows applications to run on a network server, but to be displayed on a desktop machine. Forwarded TCP/IP. This is remote port forwarding, as explained in the next subsection. Direct TCP/IP. This is local port forwarding, as explained in the next session. Port forwarding. One of the most useful features of SSH is port forwarding. In essence, port forwarding provides the ability to convert any insecure TCP connection into a secure SSH connection. This is also referred to as SSH tunneling. We need to know what a port is in this context. A port is an identifier of a user of TCP. So any application that runs on top of TCP has a port number. Incoming TCP traffic is delivered to the appropriate application on the basis of the port number. An application may employ multiple port numbers. For example, for the simple mail transfer protocol, the server side generally listens on port 25, so an incoming SMTP request uses TCP and addresses the data to the destination port 25. TCP recognizes that this is an SMTP server address and routes the data to the SMTP server application. This figure illustrates the basic concept behind port forwarding. We have a client application that is identified by port number X and a server application identified by port number Y. At some point, the client application invokes the local TCP entity and requests a connection to the remote server on port Y. The local TCP entity negotiates a TCP connection with the remote TCP entity such that the connection links local port X to remote port Y. To secure this connection, SSH is configured so that the SSH transport layer protocol establishes a TCP connection between the SSH client and server entities with port numbers A and B, respectively. A secure SSH tunnel is established over this TCP connection. Traffic from the client at port X is redirected to the local SSH entity and travels through the tunnel where the remote SSH entity delivers the data to the server application on port Y. Traffic in the other direction is similarly redirected. SSH supports two types of port forwarding, local forwarding and remote forwarding. Local forwarding allows the client to set up a hijacker process. This will intercept selected application level traffic and redirect it from an unsecured TCP connection to a secure SSH tunnel. SSH is configured to listen on selected ports. SSH grabs all traffic using a selected port and sends it through an SSH tunnel. On the other end, the SSH server sends the incoming traffic to the destination port dictated by the client application. With remote forwarding, the user's SSH client acts on the server's behalf. The client receives traffic with a given destination port number, places the traffic on the correct port, and sends it to the destination the user chooses. A typical example of remote forwarding is the following. You wish to access a server at work from your home computer. Because the work server is behind a firewall, it will not accept an SSH request from your home computer. However, from work, you can set up an SSH tunnel using remote forwarding. So here's a summary of what we've covered: the transport layer security, the web security, HTTPS, and SSH. Please take a moment to review the slide. Thank you for listening. Bye for now.